Hi, welcome to my final project presentation video. So in this video, I'm gonna go through like what my project is about, and I'm gonna start off with the abstract. So basically, this project is about like visual odometry, basically determining the trajectory or like direction of travel of a camera, like but using only RGB images. So we will only be using one cameras to determine like the distance that the camera has traveled, as well as the direction that it has traveled in. So what the technique we'll be using is Nister's 5-point algorithm for essential matrix estimation. Basically, what we're trying to do here is estimate the essential matrix, which is kind of similar to the homography matrix we learned in class. We're going to use a feature detection algorithm called FAST, which is kind of like the orb features, to detect the features, and then to then use LK optical flow to find the corresponding key points in the next image. And then using those key points, we can basically find the essential matrix using ransack. And then from that essential matrix, we'll be able to extract the rotation matrix and the translation vector to be able to determine or like how far the camera has moved and in which direction the camera has moved. And from that information, we can basically form a trajectory of where the camera has moved in like a video. So let me just run it. So basically, this is the trajectory image that tries to draw the trajectories. This is the LK optical flow. Those are the flow vectors, and that's the key point that's the algorithm is detecting. And then from those key points and from the predicted key points in the next frame, we use the key points to basically find the essential matrix. And this is the trajectory that's been drawn. The green trajectory is the trajectory that is predicted by the algorithm, and the red trajectory is the reference trajectory. As you can see, the green trajectory will kind of start to deviate from the red trajectory as time moves on. And yeah, so basically the metric that I use to calculate the how accurate this algorithm is mean squared error. So basically mean squared error in this case is just the L2 norm between the actual XYZ point, the ground truth XYZ point, and the predicted XYZ point. So the mean square error is just the average distance between the predicted point and the ground truth point, which kind of tells you how like whether or not the prediction is off by a lot, or yeah, and the unit is in meters. So as you can see, as time progresses, you can see that the predicted trajectory kind of deviates from the reference, well, from the ground truth trajectory, but it's still pretty close. So it is pretty much correctly predicting the distance traveled by the camera and the orientation of the camera. And yeah, this is my final project, and the application for visual odometry is yeah, it's very wide. It's used widely in robotics, in self-driving cars, and also for camera calibration, for determining like the speed of a vehicle, or like the distance the vehicle has traveled, etc., etc. So yeah, this will be a short presentation video. Thanks for watching.